Hello, Tensor friends. I needed to do one more video to complete my studies of the Gaussian curvature, and I need to put that in some context. All right, so what we've done up to this point through the six tedious, grueling videos was we were looking at extrinsic curvature. So the way we were doing that is we defined a vector in this Cartesian, the frame, and we were calling this the ambient the space. And this vector was a function of this angle we called the theta from the North Pole, and this angle phi, which swings around the equator, and we had a fixed length of this vector. We put a point on that vector, and then we put a sphere where we could move that point around on this sphere, okay? And at that point, we defined a tangent plane. Okay, so there's a plane that just touches right at that point. And then we found the surface, the basis to vectors. So this is the embedded space, and this is the ambient space. So we found these embedded, the basis to vectors on this tangent plane. And we also found a normal to that so we could complete our calculations. So everything we did here was us looking at it from above. So they call this the bird's eye view. So we're saying we can calculate the curvature by being out of the frame, right? Well, Gauss, he finally said, let's get some of this stuff off the board so it's easier to see. He finally said, well, why do we need that to be external? How come we can't just determine the curvature by being on the surface? So what if we're just walking around on this surface and we have a ruler, a measuring stick, and we can determine the lengths and distances and areas and angles right on the surface? And that's called intrinsic the curvature, and that's when the metric tensor was developed. So if you can find a metric on this surface, then you can start to measure the curvature of this surface. So that's what this video is all about. Okay, so this video is about the Theorema Egregium, Latin for the remarkable theorem. So it's going to relate the extrinsic curvature tensor to the intrinsic Riemann curvature, the tensor. So what I've been studying is Professor Grenfield's book, Introduction to Tensor Analysis and the Calculus of Moving the Surfaces, Professor Fowler's YouTube channel, Tensor Calculus. I also did lots and lots of internet searches on these two words. So I put all this together, and I think I understand it. I think I do. Okay, it starts with the commutator of the surface covariant derivative of the shift tensor. Now, we define the shift the tensor in the video number 1 of the curvature the tensor, the playlist, where it is related to the surface, the basis the vector, via the ambient basis the vector. Okay, so this is the shift tensor. Now, a commutator is written like this, bracket A comma B, means A acting on B minus B acting on A equals something. So if these were numbers like 2 and 4, you can see that would equal the 0. But for operators, especially like the covariant derivative, it isn't necessarily going to be 0. All right. So here's what we do. We take the commutator of the shift the tensor. So we're going to have the covariant derivative of the beta acting on it first, and then alpha first, and then beta. Okay. So now we have to say this equals to something. All right. So let's look at this, and we have to go by the rules of tensor calculus indexes. So we've got 3 free indices here, alpha, beta, and gamma. So we have to use those on something. We're going to call this something R for obvious reasons. We've got our index, our ambient index on the shift the tensor. So we carry that over. But now we have to have something down here and something up here. So this is going to be our summation index, our dummy index. It's going to be delta. Okay. And why is it negative? Because we're taking the covariant derivative of covariant indices. Okay. The covariant derivative of covariant indices is going to give you a negative. If they were contrary, it'd be a positive. Okay. From the video number 6 in the series on curvature, the tensor, we define this thing. The covariant derivative of the shift tensor can be equal to the components of the normal vector times the curvature tensor. So this is the first time we saw the curvature of the tensor. It was in the very last video, number 6. So now we can take this expression and put it right back in here after we juggle some indexes. Okay? So now these are products, so we have to do the product rule, and that would look like this. So it'd be the first times the derivative of the second plus the second times the derivative of the first. Then we got the negative sign. Do the same thing. It's still equal to the same, whatever this stuff is. Okay? Now, here's something I did not derive in the 6 videos. I should have. I didn't. I don't know why I didn't, but I didn't. It's called Weingartner's formula. I'm going to leave a link to specifically this derivation in the description if you're interested in it, which shows that the covariant derivative of the normal component is equal to the negative of the shift the tensor times the curvature of the tensor with the upper and lower index. Okay, so now you can see we can use this everywhere we have one of these. There's one there, there's one there. So let's bring those down. So here's the expression, and we're going to plug this in with the negative sign everywhere you see this. So I put it in there, it changed the sign. I put it in here and it changed the sign. Okay. Now what we want to do is isolate this by itself. So how do we do that? Well, we can dot both sides of this equation with the inverse shift the tensor. Now, I run out of indexes here, so I have to come up with a new one. You can't use the same one because you've got all your free indexes are taken into account, and you've got 2 sets of summation indexes. Okay, so I chose Z epsilon I. So we dot both sides just like this. So I just put it in everywhere. Boom, 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 boom. Now, here is something that we found out in video number 1 and 2, I believe. Number 1 and 2 is that, well, you know this, the inverse shift tensor times the shift tensor is going to give you the Kronecker of the delta, right? So these I's contract out, and you get epsilon, I don't know if contract's right, absorbed out, you get epsilon the delta. And the component of the normal vector dotted with the shift tensor is equal to 0 because the normal normal component is of this vector, the normal vector, and it is orthogonal to the surface basis vector. So if it's orthogonal, it's equal to 0. And the surface basis vector is related to the shift the tensor via this. So if this is true and related in this manner, then this must be true. Okay, so that's back in video number, this is in video number 1, this is in video number 2. Okay, so we can put these 2 things in all of this stuff that we just did. So as an example, in this one here, right, we're going to get a Kronecker the delta here. We're going to get a Kronecker delta here, and we're going to get a Kronecker delta here. But everywhere you see a normal component dotted with a shift the tensor, then this applies. So that goes to 0. This one goes to 0. So we're only left now with 3 terms. Okay. Now we can just cancel this from both sides. Like this is gone, this is gone, and this is gone. So now we have an expression between this tensor and these tensors. Okay. And I copied it down again. I don't know why I did that. So this is the Theorema Egregium. Okay. So it is relating intrinsic curvature can be found by these products of extrinsic curvature, which I think is just really, really cool. All right. Now let's actually look at some examples of this. Okay. In one of my videos, I'll leave a link. I did uh, the surface of a sphere. So we held the radius constant. We found the metric tensor, the Christoffel symbols, and the Riemann tensor components for the surface of a sphere. I'll leave a link to that. Okay, so we go to that video. We get the Riemann tensor, just one element of its matrix. And I just chose this one. So it was r the theta phi. So there's only 2 variables because it's the surface of the sphere. It's just exactly like we've been doing on the curvature of the tensor. We're just looking at the surface of the sphere. And the answer was sine squared theta. All right, now let's look at these indices, okay? So you can see how I've got delta, gamma, beta, alpha, beta, right? So in this case, the delta is theta, the gamma is phi, the alpha is theta, and the beta is phi. Okay? So that accounts for all 4 of these. Now we go back to video number 6, and we did all these. We had the curvature tensor expressed like this as 2 covariant indices, and we had it expressed like this with the mixed indices. We had all of these components. So if we follow these rules set by this one I chose, then we get this minus that, and these mixed ones now are all 0. So b a phi is minus a sine squared theta, and b with the mixed indices is minus 1 over a. So you can see what this does. The negatives cancel, the a's cancel, and we get sine squared theta. So we calculated the exact same answer for this component of the Riemann, the tensor, by using the curvature tensor from the extrinsic, the point of view. So I just thought that was really, really cool. All right. So that's it. Thanks for watching. I'll see you later.